In episode 68, we talked about this dual pixel technology from Samsung, which is used for face detection autofocus. This is legacy, not very old, sort of sensor array where you have RGB filters, but occasional pixels are dedicated to phase detection. Samsung fills in, every pixel has this dual pixel technology, and there's a lens lid on every resolving element that images onto the split pixel. And the idea is to detect the local defocus. So basically you're detecting the coherence measure of the field. They do this in various orientations. What's exciting to me about this technology is it indicates this oversampling relative to the lambda f number to get extra information. In this case, trying to get the defocus, but we could imagine using this to measure more interesting projections of the mutual intensity. Here's a little sketch that I made of a multiple sensor pixel, but in this case, imagine that the little subpixels are connected interferometrically. And so if you go to Dolly, explain that's what you want to do. This is one of the versions of a little interferometer array that Dolly put together for me, and another version. So imagine that you're coupling into a set of waveguides, and then the waveguides are interconnected in some kind of fabric. Here's yet another version of this kind of non-irradiance detecting array where you're going to detect the field and then using some kind of interconnectivity like this, a Mach-Zehnder interferometer, interfere adjacent pixels with variable mixture coefficients and variable relative phases. This kind of integrated interferometer has a lot of precedence. A lot of groups have tried to look at various ways to either use optical waveguides or in this very interesting article, using a electronic plasmonic waveguide to create a little integrated micro interferometer. Today, we're going to talk about how those could be used to create coherence focal planes. Computational imaging. Episode 70, Interferometric focal planes. The little video that I showed back in episode 52 of light propagating through a sequence of lenses. It's kind of a crazy video that was made by Sora, but here's a simpler version that's a sketch of a lens waveguide. So we have a set of lens waveguides actually with light going through. And then the point of a lens waveguide is that light would propagate through without any degradation, that after you have the initial bandpass of the first aperture, as you go through successive apertures, light is no longer degraded. This is easy to understand in a coherent waveguide. So here's a sequence of lenses, and let's say that they're each separated by a couple of focal lengths. The image of, if over here if I have an object f of x, of course, f of x is low-pass filtered and going through the first imaging system. So here, the field distribution would be the input field distribution convolved with the sink. Now, if you go to successive steps through the lens waveguide, you convolve again for a sink, but convolving a function that's already been convolved with a sink recovers the original convolution because the sink has a flat bandpass. So if you multiply the transfer function after each lens, the transfer function is constant across the spatial frequency range, and the image that you have here after the first lens is repeated without any degradation after each successive lens. Now, this is from episode 52, and so we talked also about what happens in an incoherent lens waveguide. So we've seen that the irradiance that you have from an incoherent object forming after the first lens, the image that forms of this remote object f of x over here, is the remote object irradiance convolved with the square of the coherent impulse response. So that in this case, that would be sinc squared. Now, if you went through successive versions of the lens here, go through successive stages, if you reconvolve with sinc squared, of course, the field would be degraded, so that the field would be degraded after each lens. So you have the triangular bandpass that we have with the coherent system, the Fourier transform of the sinc squared. If you continue to multiply by the triangular bandpass, your bandpass would be degraded after each lens. But This is not what happens in reality, because we don't measure the irradiance. What we measure is nothing. Here, after the first lens, in this lens waveguide, we have the field distribution from f of x here, but it's described not by the irradiance, but more completely by the mutual coherence function. And then if we go to successive stages of the lenses, the mutual coherence reappears. And the reason that it occurs this way is because the mutual coherence is convolved with the sink in x1 and the sink in x2, so that passes without any further degradation. The same is for a coherent system. Now you could think of this as saying, well, the incoherent system is a superposition of coherent modes, and that's a correct way to understand what's going on here. But basically, the main point is that if we don't measure the irradiance, if we just pass the field through the lens waveguide, the incoherent system behaves the same as the coherent system. So it's the act of measuring the irradiance that destroys information, that there's less information in the irradiance than there is in the mutual coherence. This leads to, of course, the very interesting question from a system designer point of view, saying, well, if there's information in the mutual coherence, could that information be measured? Could we pull it back out? We continued discussion of this back in chapter 8, where we talked about the mutual coherence transfer function. So this is an image from episode 51, where we looked at what does the transfer function from the remote incoherent field distribution to the focal mutual coherence look like. And so it turns out to be the ambiguity function of the pupil, and we looked at its properties back in episode 51. We can also look at, well, what does the distribution of the mutual intensity look like when we get into the focal volume. And here's an image for a sinusoidal remote f of x. So f of x in this case is 1 plus cosine of 2 pi ux. And so what you see along the diagonal here is what you would measure with the irradiance. This would be j of x1, x2, but x1 is equal to x2 along the diagonal. That would be the irradiance that we measure. And then if we go off of the diagonal, we're measuring j of at x and delta x. Here's a plot of what these lines look like. So the top plot here, that's the when x1 is equal to x2. That's the diagonal here. That's the irradiance that we would measure in imaging this remote sinusoidal signal. But now if we go up here, we're going to make x2 equal to x1 plus 0.75 lambda f number. So we're looking at a plot that may be up here. Now what you see is that the oscillations are about the same height, but the baseline, the offset has been reduced. So this would help us improve the signal-to-noise ratio in estimating the high-frequency component of this signal, because its amplitude relative to the DC has been improved. And if we go even further and say x2 is equal to x1 plus x plus 1, then we're going to be actually somewhere even closer to this range here. But you see that now there is no offset, that the low frequency component of the signal is 0, and we only have the high frequency modulation. So we've been able to isolate the high frequency modulation. So then to measure this, we're measuring the mutual intensity at a position and a position with a step size delta x. So we're measuring the coherence between 2 points separated by 1. Now the problem, of course, we have is that we can't directly measure the mutual intensity. We measure intensities always, but we can measure transformations of the mutual intensity. And the question is, could we come up with some transformations that get this kind of advantage that would suppress the low frequency part of the signal relative to the high frequency to improve the high frequency signal to noise ratio? Now, as we talked about in the introduction with, for example, the Samsung dual pixel technology, there is precedent for systems that measure some form of coherence projection near the focal plane. The most common one is this idea of planoptic cameras, which are used primarily to look at focal stacking or high depth of field imaging. But really, if you analyze what they're doing, they're measuring some kind of coherence projection of the main image. In this case, you're thinking of it as defocus, but it's really a kind of coherence projection. One problem with it is it's not really adapted to try to get this high frequency signal that we're trying to get. There's also been examples of plasmonic devices that implement various kinds of coherence projections of the field. Here's an example of a grating, a metamaterial grating placed on a sensor that has an angularly sensitive response, which means it's sensitive basically to a coherence measure of the field. And this in the left is a clear aperture image of an object, and then the object image through one of these devices where you see a angularly dependent high frequency filtering of the object. So it's, again, the sensor is measuring a kind of coherence projection of the field. What we would like to imagine is that we could make a adaptive interferometer. So that in this case, this is a simple picture from this group in India of what a Mach-Zehnder interferometer looks like, but with two ports. So we have two input ports, E in here and E in here, and we have two output ports, and we have the ability to adjust the relative phase of the signal on each port and adjust the coupling ideally to create an arbitrary transformation of the field between the two ports to allow us to measure their mutual coherence. So this is an ideal sort of device, and what we know from the fact that there is missing information when we measure the irradiance instead of the mutual coherence is that it would be useful if we could measure the coherence projections of the field. We're going to imagine that that's true. Let's imagine that we have this kind of two-port interferometer, and then consider what that would mean for imaging systems. So what I showed you with the plot of the mutual intensity was plots of J as a function of position and spatial displacement. Let's imagine that we have this kind of two-port interferometer where we can extract the field at point Y and zero displacement. This is J decomposed into mean position and delta X as we've used it quite commonly. And then we have the field drawn from a second point, again with zero displacement relative to itself, but then we take those 2 points and we interfere them with each other. So the off-diagonal terms of this mutual intensity matrix are the interference between the two sampling points. We're sampling the field at point Y, X bar equal Y, and zero displacement, X bar equal Y plus delta, and then we're interfering the field between those 2 points. Now, the way we interfere the field and make measurements is we can transform the field through this Mach-Zehnder interferometer. So this H matrix mixes those two modes, and then we measure the diagonal of the transformed J matrix in measuring the irradiance. So the output ports of the interferometer measure the irradiance at those output ports. This H matrix is familiar to us from way back in episode 29 when we talked about two-mode phase retrieval. So we can have a mixture amplitude, cosine theta and sine theta, and a relative phase between the modes psi. As we mix them in the interferometer, we can implement. Now, in episode 29, we talked about doing that on a couple of coherent modes. If we think about doing it on a mutual intensity matrix, we operate on the modes from the left and the right that have created this kind of matrix through their outer product, basically. And then that creates a new rotated mutual intensity matrix where we measure the diagonal to get these measurements. Now, we, back in episode 51, derived this transfer function for J. And the reason we could do that is in this parameterized version of J, where we consider the mutual intensity at X bar and delta X, the transformation from a remote incoherent object to the mutual intensity is shift invariant. That allowed us to derive the transfer function. Since J is shift invariant, G, which consists of sums of the terms in J, is also shift invariant. So we can take the Fourier transform of this transformation for some input remote distribution f of x and get the transfer function for the terms of G. Now, G has two output ports, so there's two transfer functions. And if we go through the math and derive what they look like this. You recall that the transfer function for J in one dimension is basically magnitude of this 1 minus magnitude of U times the sinc. Now, because of these mixture terms, we've created a somewhat more complicated version of that transfer function. But this is our transfer function between in each of the modes of the interferometer. This transfer function is analyzed in this notebook that's on the GitHub site. I've been working on this series of GitHub materials for about 5 years. Within that 5 years, life has changed because the emergence of large language models has fundamentally changed the way we do analysis and programming. So a lot of the things from the last 6 months are using discussions with large language models, and this particular notebook used Google Gemini very helpfully to create the plots that I'm going to show you. But here's what they look like. So this is the transfer function for each of the arms of the measurement matrix as a function of this mixture angles theta and psi. If we set theta and psi equal to 0, we're just measuring the intensity at each of the sampling points, and the transfer function looks like the standard one-dimensional incoherent transfer function, this triangular transfer function. But as we change these, the coupling coefficient theta here, we set, well, we varied psi in one of these, I guess. But what you see is that we get, actually mostly the same transfer function on the T1 arm, but on the secondary arm where we're doing the mixture, we see wide variations in the transfer function, and we see for some regions of frequencies the transfer function can exceed the incoherent limit, which is obviously super interesting and useful to us because we have the ability to locally vary the transfer function to try to match features in the image, and we can implement multiple transfer functions by changing the parameters dynamically to try to improve the passband of this system. Now, back in episodes 53 and 59, we talked about pupil modulation to try to play with the transfer function and increase the high frequency bandpass. This was an example where we used a folded annular aperture to try to suppress low frequencies and improve the transfer function at high frequencies to improve SNR. That worked, but to a relatively limited extent. Here we're seeing much more dramatic changes in the transfer function by using this local interferometry. So the goal again is basically to characterize mutual intensity, which we are able to do by varying these parameters. But we can understand why that's advantageous because we're trying to get to this higher frequency passband that's consistent with the passband for the mutual intensity, but not consistent for what happens to the irradiance. Now, you might say, well, could we make it so we suppress the zero frequency altogether and have a transfer function that looked like that? That would certainly be a powerful and wonderful thing to do, but unfortunately, it's impossible. And we know it's impossible from Bochner's theorem from harmonic analysis, which says that if we have a positive measure, which is in the case of a irradiance measurement system, we can't measure negative numbers, so we have a positive impulse response. And so its Fourier transform has to be, it turns out, positive definite, and positive definite has this definition, but one of the implications of the transfer function being positive definite means that the transfer function at zero frequency must exceed the transfer function at all other frequencies. So the peak of the transfer function always has to be at zero frequency, but we can improve it at other frequencies relative to what we get with the standard impulse response. This analysis again was done with Gemini, and Gemini suggested that I should show you a graphic. And so this is the simple graphic that Gemini made. The main point is that here's this limit at 0, and everywhere else has to be below that limit. So I'm not sure that this graphic is particularly useful, but it does emphasize this point. But it gives us a lot of things to play with to try to get more information. And so we've gone and analyzed this in more detail in this paper, which is available at the link shown here, and it should be published soon in Optics Express. Here we're imagining that the unit cell of a focal plane consists of these 4 points, that these black squares are points where we're going to draw modes from the field. And then we want to analyze our ability to estimate the separation between 2 points. So the red and green points here are the points we're going to try to estimate their separation. This kind of hazy stuff around the black points indicates the kind of mode we're sampling at each point. We're also going to try to get the orientation of a line. So the blue thing here is the line. We try to get the angle of the line through the unit cell. Imagine that we have a corner in the middle of the unit cell, and we can try to say, could we estimate the orientation of that corner by analyzing the coherence functions. If we talk first about the 2 points, you can imagine that you have a point source position at plus and a point source at position minus. With the Rayleigh criterion, they could blend into a single impulse response, but we're trying to separate them using this interferometry. So we have these 2 point sources. So the point source at position plus creates a excitation A plus in the first mode that we're measuring from our sampling point, and creates a excitation B plus in the second mode. This point source at position minus creates an excitation A minus and B minus. So if we were measuring only the intensity, we would measure this term and this term, the sum of the irradiances from each of the point sources. But because we have this possibility to measure J, we can always also measure these off-diagonal terms, A plus times B plus and A minus times B minus. Now, the point sources are mutually incoherent, so we don't see terms in their product. But if only one point source was present, we would only have this A plus, B plus, and A plus times B plus terms. But because there's no real phase from a single point source, knowing A plus squared and B plus squared would also tell us what A plus is, so we would know A plus times B plus. But because there's 2 point sources, this sum of these 2 products is a linearly independent, or it cannot be predicted from knowing just the irradiances, and so we get extra information by trying to find those off-diagonal terms. Now, if we imagine that the 2 point sources are Gaussian modes, or basically any other kind of mode, as we saw back in chapter 7, the eigenvalue of this matrix, the eigenvalue of the J matrix, will go like the delta squared. So delta here is the separation between the 2 point sources, and here we're calculating this matrix and looking at its eigenvalue as a function of the separation. And it turns out that it's proportional to delta squared, which means while we plot it on a log plot, we see this line, and then the slope of the line is 2. So, but now, instead of like moving an interferometer or the other methods that we looked at back in chapter 7 and 8, we just have an interferometer, and we're going to electrically adjust the relative mixing of the interferometer, and we can distinguish the separation of 2 point sources. So in the paper that I referenced on interferometric focal planes, we do Monte Carlo simulation of this system. So the bottom curve here, the green curve, is estimation of the 2 point sources, or the separation of the 2 point sources for various values of x1. So x1 and x2 are fixed positions of the point sources. We don't assume that their mean is anywhere interesting, but we're taking x1 and moving it around the unit cell. And then the red curve, the fixed strategy, assumes that rather than dynamically trying to set the mixture coefficients of the interferometer, we have 3 fixed coefficients. So we try to go through fixed transformations and measure the mutual coherence without adaptation, and then use those parameters to in a maximum likelihood estimator to estimate the separation. And then the top curve is using the irradiance alone. And very similar to what we saw back in chapters 7 and 8, if we do this adaptive interferometry, we can exceed the estimation performance of the conventional irradiance measurement by a couple of orders of magnitude or more. The underlying thing going on here, of course, is that we're able to vary the PSF and adapt the PSF to the source to try to improve SNR for getting these high-frequency coefficients. But you could look at, well, how does this work if we estimate other parameters? And so we tried estimating the orientation of the line. And this is for various intercept points of the line. And we didn't find in all cases that interferometric measurement exceeded the performance of the intensity, because in some cases where it's a simple geometry, the intensity may have sufficient degrees of freedom to estimate the underlying parameters. But in many cases, in many orientations, we did find that the intensity did better. Now, of course, if you made the optimal adaptive strategy, you would never really do worse than if you just measure with a non-adaptive system. Here, it's not really an optimal adaptive strategy. The adaptive strategy is just trying to find the eigenvalues. And we see similar kind of behavior in trying to estimate the orientation of a corner. This is a developing and interesting area where nobody has built this kind of interferometric focal plane, and the closest thing would be things like that dual pixel auto detection. But there, the data hasn't really been interpreted in this way to think about what it would mean if it was taking coherence measures. The point of this discussion is just to point out that it is possible that, first of all, there's extra information in the field that's not being measured, and it is possible to design focal planes that could measure it. Now, focal planes in general are terrible. That the temporal sampling, as we've seen, is not intelligent. The spectral sampling is not particularly intelligent. So there's just enormous room for continued improvement. And one of those improvements, of course, would be to imagine focal planes that can make coherence measures. But of course, this has all been at a single frequency, and real fields consist of broad spectral features. So it would be most interesting to consider interferometric sensors in a focal plane that maybe had response to polarization, spectra, and more interesting temporal response. And so hopefully what we've seen in the series of lectures for the last 10 or so episodes is that it's possible to reimagine how we sample fields if we do computational imaging, and that it would be worth the effort to reimagine it. So this brings us to the end of a certain phase of this project. So these episodes are all based on the upcoming textbook, Computational Optical Imaging, that will be published by SPIE Press. And unfortunately, SPIE Press has not completed editing to release it, but it should happen hopefully in the next few months. The episodes have gone through about 7 to 8 episodes on each chapter. So the first chapters, episodes 1 through 11, covered forward models. The next 7 episodes, episodes 12 through 19, covered inverse problems and estimation. Then we went through geometric imaging and coded apertures in episodes 20 to 26. Episodes 27 to 34 went through wave imaging. If you go back to the beginning of these episodes from over a year ago, there's a little bit of a different outline of the text. That's because reviewers came and said, gee, you've talked a lot about coherent systems, but you didn't talk that much about incoherent systems. And so the impact of that was to divide chapters 5 and 6 to make 2 chapters on coherent imaging. And so episodes up to episode 40 went through coherent imaging. And then a lot of material was added on these topic of today on optical coherence and how novel sensors could improve measurement by considering optical coherence. So we've gone through, the episodes going through digital sampling, and today's episode completes chapter 10 on sampling strategies for focal planes. The next final chapter, chapter 11, is design examples. But I think we'll take a break from creating episodes. We've come to the end of the term at the University of Arizona, where this course is taught, where we go through a couple of terms on computational imaging and computational photography, and happily the term is about to end. So we may wait a few months to create the final episodes that talk about optical design, because there's a lot of interesting devices coming out of the work coming in here that will go into design, and we'll create some more episodes to describe them this fall. Now, again, this work happened at the College of Optical Sciences at the University of Arizona. Here's a image from episode 62, where we blended two images of the college and fused them together. Over here is the original Minell building and the Minell extension that opened in 2005, and the Grand Challenges Research Building, where my laboratories are. These episodes are not for the faint of heart. If you've watched these 70 episodes and understood them, then either you are, should be, or have graduated from graduate school in optics. And if you find this interesting, then you probably belong at the White College of Optical Sciences, and we would love to see you there.